We would like to show that the following limit does not exist. The limit as xy approaches the origin of the function xy squared over x squared y to the fourth. So we want to show that there are different paths along which the limit will give different values. So if we take the limit along an axis, that means that either x equals 0 or y equals 0. Then that means that this function xy squared over x squared plus y to the fourth will just equal 0. For example, if we let x equal 0, then we'll get 0 over y to the fourth. And if we were to let y equal 0, we would get 0 over x squared. And both of those are just 0 as long as the other variable is not 0. And since xy is approaching 0, 0, if we allow one of the variables to be 0, the other one is not 0. Because in the approach, we're assuming that this point is different from 0, 0. Okay, so if we approach along an axis, we can call that path 1. Then the limit is 0. So path 2, and another natural choice for a path, is along a line. Y equals mx, we're approaching 0, 0, so y equals mx would approach along some line of slope m. And if we put y equals mx into the function, so f of x comma mx is x times mx squared over x squared plus mx to the fourth. And if we simplify this, it's mx cubed over x squared plus m to the fourth, x to the fourth. And we can cancel an x squared, leaving us with mx over 1 plus m to the fourth x squared. Factor in x squared from the bottom and cancel with x squared on the top. Now as xy goes to 0, 0, our point is on this line, so there's xy that goes to 0, 0, then that means that the x is going to go towards 0, and so the numerator goes to 0 and the denominator goes to 1 plus 0, and so the limit is 0. But that's the same as it was for path 1, so path 2 doesn't give us any new information. So that's the same, and according to our understanding of a limit, we have not yet shown that the limit doesn't exist. In fact, we might have sort of convinced ourselves that the limit is 0. But there is another path that we can consider, path 3. We notice here that the exponents on x and y are different. And it helps if we can make everything have the same degree here. So I would want this y to be a square root of x. So that would become x squared. Or equivalently, we would want this x to be y squared. So let's let x equal y squared. So we're approaching along the parabola x equals y squared. The sideways parabola. So our point xy is somewhere on this parabola and approaching 0, 0. It could be in the first quadrant or it could be down here in the fourth quadrant. And if x equals y squared, then the function, which is here, x squared, y squared. So x is y squared, so this becomes y squared, which is y to the fourth. And x squared becomes y squared squared, which is y to the fourth, plus another y to the fourth. And this is 1/2, as long as y is not 0. And if our point is on the parabola x equals y squared, and the xy is not 0, 0, then the y itself is not 0, because the x is not 0. And then the y is plus or minus the square root of that x, so definitely not 0. So our function that we would be taking the limit, we are taking the limit of, is just the function 1/2 if our point xy is on this parabola. So that means that we will get different limits depending on the path chosen. So the limit as xy goes to 0, 0 along the path x equals y squared of our function is 1/2, which is not 0. And so again, different paths yield different limits, and that tells us that the limit does not exist. So the trick here was that the path needed to be x equals y squared. We would like the numerator and the denominator to have the same degree. And right now the numerator has degree 3 and the denominator is degree 4. But if we let x equal y squared, then as you can see here, we get degree 4 on the top and we get degree 4 on the bottom. And so we get some simplification to the non-zero number 1/2. The other paths yielded a limit of 0, and so the limit does not exist.